actually going to introduce the space that we're going to be working with most of the time. So when you're doing calculus 1 and 2 and algebra and calc, you're usually working in the xy plane, right? So it's just a two-dimensional space, and you're usually working with one-dimensional curves. Now in Calc 3, we're actually going to up the dimensions a little bit, and we are going to be working mostly in a three-dimensional space and working with 0, 1, two-dimensional things usually, or solid objects, but we can think of them as two-dimensional closed surfaces. And so we're going to sort of introduce the space that we're going to work with, and that's where we're going to start. So this is 10.1. Okay, so let's remind ourselves about 2D. Back when you're doing algebra and pre-calc and all that stuff, how did you actually locate a point? How did you find the address of a point? How did you find it? What did you do? An ordered pair. How was it ordered? Right? Well, there's the horizontal axis, which we call the x-axis. There was the vertical axis, which we call the y-axis. And if you wanted to locate a point, all you do is you find the point right below it on the x, that gives you that. And then right beside it on the y, that gives you that. Right? And you sort of locate it by these ordered pairs. So if the number on the x-axis was a and this was b, then the address of this point was a comma b. Right? That was how we did it in 2 dimensions. For 3 dimensions, it's very similar. Throw it in. And we use an ordered triple. Right? So this idea is the following. That's your x, this is your y, and we call the third axis the z-axis, right? And of course, there's a negative part that goes in the back, and this goes down as well, right? And a point in this space is located by 3 coordinates, right? So you move right under the point on the x, that's the A, and then you sort of figure out what y values beside that point. And you sort of make these 3 come together, right? The A, the X, the Z, and the Y. It comes right below the point. And so the coordinate here is A, comma B, comma C. Right? So I was thinking of one of the best ways to actually talk about what this space looks like. I asked Nettie to try to make a model of the 3-dimensional space, and she jacked some papers together and couldn't come up with anything.
You didn't give me scotch tape.
She was like, I'm not Japanese, they do the origami stuff. Okay, alright, so probably one of the best ways, and the ways your textbook do it, is they actually use a room to illustrate, so I'm actually going to use a room to illustrate as well. Okay, so technically you don't have to draw it in this orientation, but this is the standard way in your textbook. When they draw it, this is how they're going to orient it. You just have to make sure that if you're sort of standing on the xy plane, so that the z is actually going towards your body, then to go from the x to the y, you should be moving counterclockwise, right? So whichever orientation you draw, make sure at least that is true. But this is the standard way to draw it, and this is the way your textbook is going to draw it most of the time. The x is going to be over here, y is going to be over here, the z is going to be over there. And now we're going to introduce what's the so-called coordinate planes. Right? So you have the same sort of space, x, y, z. And the idea is, if you sort of think of this as the corner of a room, you're going to have like a wall going here. Right? And there's going to be another wall coming along this one, and then there's going to be the floor. That's sort of the room model. And this plane here, that's subtended by the x and the z, you call that the xz plane. Right? This one here, that's the y and the z, is called the yz plane. And the xy plane is the familiar xy plane that you've all been used to. That's another definition. So this is the idea, right? So this is how the space that we're going to be working with sort of looks. So pretend this corner is actually the axis, right? So this is the z-axis running up along the edge of the wall here. Your x-axis would be running along the floor where the wall and the floor meet. Your y-axis will be running along where the wall and the floor meet, right? This wall here is, this is z, that's x, so this is the xz plane, right? This flat wall going right along that is the xz plane. This would be the yz plane. The floor that we're standing on is the xy plane, right? The actual room that we're in is called the first octant, right? So this is where your x values all have positive values running along that wall. Your y values are all positive here. Your z values are all positive here. We're in this space where everyone's positive. It's called the first octant, right? It's called octant because there are 8 of them in octant. Right? So that's the idea. And this roof is actually not there. In general, you can expand forever. But let's say, how high do you think this roof is? How high do you think this roof is?
14.
Like 14 feet? Okay, so let's say we're measuring units in feet. The roof would actually be the plane z equals 14, right? And we're actually going to talk about that a bit later, right? So this is our first octant, right? We're x, y, z. So that's the idea, and that's how they sort of use the room model. I wanted to make like a paper model of this so you can see it, but maybe let me down. Okay. Another thing you need to know about these coordinate systems is just as how you can think of the y-coordinate as the distance from the x plane, distance from x-axis. The x you can think of as the distance. So absolute value A would be the distance from the y-axis. Absolute value B would be the distance from the x-axis. A similar thing is told for the coordinate systems here, right? So you're in ABC, let me actually rewrite this. And this here is. So when you look at the 3 coordinate system A, B, C, this is the so-called x-coordinate. And you can actually think of it as the absolute value is the distance from the yz plane. Right? This is the y-coordinate. And the absolute value of that is the distance from the xz plane. C is, of course, the z-coordinate. And it's the distance from the xy plane. Can you actually get this?
Yep.
Okay. All right. Okay. So that's how the coordinate systems work. So these guys sort of tells you how far you're away from the YZ plane, or the XZ plane, or the XY plane, and that all comes together and makes an address. Similarly, how here you can say, tell me how far I am from the Y-axis, tell me how far I am from the X-axis, and you can actually use that to locate the point. And you put it in an ordered pair. You can do a very similar thing in 3-space, and so on and so forth. So, just sort of introducing the space here that we're going to be working with. And let's talk about some simple planes here. That are introduced in 10.1. We're really going to get into planes more in depth in 10.4, I think. But for now, so the coordinate planes are some of the simplest planes you'll ever see. Which, by the way, I should probably give you the equations for those. So remember we said there was something called the XY plane. And the equation that describes the XY plane is who knows what equation describes the XY plane?
Z equals 0.
Z equals 0. Right? So remember, this guy is just like an axis. It measures the values of Z. Right? These are all positive numbers. When you hit the floor, you're at 0. If you go below the floor, you're negative. Right? So this is the equation Z equals 0. The YZ plane is the equation X equals 0. The XZ plane is the equation Y equals 0. Right? If you're on the XZ plane, you're 0 distance from the Y. The Y value is 0 distance. Other ones are X equals K, or Y equals K, or Z equals K, K some constant. These are also very simple planes. They're called constant planes, right? So X equals K is just a plane that is parallel to, what do you think X equals something would be parallel to?
The YZ.
The YZ, right? So again, if we're thinking of this as the x-axis, then when you get to some x value, right, like x equals 2, right? All points where x equals 2 have to do what? Fall along the line I'm walking here, right? Because if I move to the right or to the left, I'm not at x equals 2 anymore, right? If I trace back to the x-axis, I'm at a different value. So to maintain the value of x equals 2, I have to walk in this line. If I'm a plane walking in this line, I'm parallel to that wall. That wall is the YZ plane, right? So these are planes is of course parallel to and that's why I could tell you that the equation for the roof would be Z equals 14. Why? It's actually parallel to the floor, so I know its equation has to be Z equals some constant. The constant is just going to be whatever units I'm using to measure this distance, which if we use feet, we say it's roughly 14 feet, so it's Z equals 14 is that equation. Right? So once you're at that level, you can't come down or up because you changed your Z coordinate, right? So you have to maintain that level, and hence you'll be parallel to the floor. The roof is Z equals 14, right? So something like x equals 2, if you were to do a sketch from that, you find the value x equals 2, and you are a plane. Right, running along that line. if you do something like y equals 2. Right? Just find y equals 2, and of course your plane has to be running along that line. Right? This is parallel to exactly. By the way, I mean, I draw it as a rectangle because I only have a finite board. It actually extends forever in all in things. Right? It's just an infinite sheet, right? That happens to be parallel to the xz one, right? So that's that. One thing to note here is that things are going to usually bump up a dimension. What do I mean by that is like if you have in 2D y equals 2, what kind of curve is that? What kind of thing is that?
Straight line.
It's just a straight line, right? It's a line, right? Lines are one-dimensional. However, notice that in 3D, a very distinct thing happens. If I look at the same y equals 2, what is it now? It's actually a plane. How many dimensions are in a plane? 2 dimensions. So this is going to be one thing you're going to have to look out for when you're working in 3 space. Things that look like lines before are now actually going to be planes. And we're going to define more specifically what planes are in 10.4. But for now, this is something you should be aware of, right? Things that look like constants, x equals a constant, y equals a constant, z equals a constant, they're all planes. They're flat sheets that extend forever in directions parallel to one of the coordinate planes. And they are 2-dimensional things, so that should be something that you should be aware of. Next thing I'm going to talk about is distances. But before I do that, what would y equals x look like? I heard someone say a line. You're already wrong. Right, in 2D, y equals x is a line. In 3D, it's not. It's a plane. What kind of plane is it? How does it look?
It would be
Coming straight at us.
Coming straight at us like this?
Like at me.
Right, so the x is here, the y is here. Remember in 2D, if you have y and you have x, y equals x, it's like this, right? Imagine that same thing is happening on the floor here. When that was our world and we were living in flatland, that was y equals x, right? We didn't see a full picture of what y equals x was. Now that we can go up and down, we can actually see there's an entire plane here. Right? That's going through, it cuts here at an angle that's 45 degrees, or pi over 4 from the x or y. So things like that you should sort of be aware of. Distances. How do we measure distances in 2D? Say I want the distance between x, y, and another point, x1, y1. Distance from, what's the distance from?
Square root of x1 minus x whole square.
X minus x1 squared plus y minus y1 squared. Anyone knows how they came up with that formula?
Pythagorean theorem.
Pythagorean theorem, right? Which, as of yesterday, you all should know by now, because I asked you to write it down. In 3D, let's say I want the distance between 2 points, x, y, z, and what do you think the formula is going to be now? It's pretty much going to be the same thing. It's really nice how that works out. Of course, no one actually guessed that it works out this way. You can actually prove this works out, and it's again repeating the Pythagorean formula. Right now, you just have a right triangle that is in 2 dimensions rather than. Right, so that would be the distance. That's how we measure distances here. So you just tack on another thing for the z coordinate. Something else we need to know about 3D. So in 10.1, they're just introducing the 3-dimensional coordinate system and then making some things that were familiar to you, telling you how they change in this space. So one way in which things change is that constants are no longer lines. They're actually planes now. Another way things change is that your distance formula has 3 variables to worry about. Another way is something like they talk about a sphere. More complicated shapes we'll actually deal with later on, I think in 10.6. But they actually deal with a sphere here, and they can deal with that now because to find the equation of a sphere, you actually use the distance formula. So So this here in 3 dimensions is the equation of a sphere with center ABC and radius r. And it should actually remind you of an equation that we have in 2D if you took out the z. What does that actually look like? It's just a circle. Right? So the idea is here. Let's say I made something like the center was the origin. Right? Then it's just x squared plus y squared plus z squared equals some r squared. The sphere would be here. And if you make z equals 0, you actually kill that, then in that plane you'll actually trace out the circle of radius r. And it's consistent with what we learned in 2 dimensions. So that's nice. Right? So the distance from the center to outer here is r. Right? I never told you that this was the origin, but it should probably considered obvious at this point. So the origin is where each of the three coordinate axes meet, and it's designated by the location 0, 0, 0, and I can actually draw a circle of radius r centered at that origin, and realize that if I plug in my z equals 0, this, which is called the trace, gives me a circle with radius r in the xy plane. And that's nice. These things are traces. We're going to work a lot with traces later on. So yesterday when I gave you that quiz and I was asking you to graph all these curves, there was actually a method to the madness. It turns out you're going to be able to use these curves to draw three-dimensional objects, right, by just isolating them to a plane. You actually need to know how to draw them in 2D in order to draw something in 3D. So I wasn't just giving you stuff to do for the sake of doing it. Everything I ask you to do, there's a reason why we're going to be doing it. Right? So a sphere happens to be one of those things that you could actually draw, because in the xy plane, the trace, meaning the two-dimensional representation, in the one-dimensional representation in a two-dimensional plane is just a circle. If you look in the other plane, you'd also get a circle. And if you look in the YZ plane, you also get a circle, and you sort of just revolve these circles on each other to get a plane. Right? Don't worry, we'll go over that in 10.6. But right now we're just keeping things very simple. Another thing you need to remember is completing the square. So if they give you the equation of a sphere, but it's not in that exact standard form, you should be able to recognize that it's actually the equation of a sphere. So I mean, I already told you, but I'm just going to give you an example anyway. Okay, I'll give you guys a minute to do it and tell me the answer. Yeah, you finished? What's the center?
2, negative 1, 0.
And the radius?
Square root of 5.
Okay, let's see how she got that. How did you get that?
So I finished the squares for the x, z, and y.
How did you do that? You did it from
I
that
put
form?
everything on one side.
Okay, so the first thing is to put everyone on one side and sort of group the x's together, group the y's together, and group the z together.
Then I complete the squares. Like
How do you complete the square here?
for that one, I have to add 4 on the both sides in order to make it x minus 2 whole square.
How do you know you have to add 4? Divide by 2, right? To complete the square, you add half the coefficient of the x to both sides, right? So it's x squared, I don't want to write. I'll write it out, right? Plus, you add half of this squared to both sides, right? So it's minus 4 over 2 squared, you add that to both sides. Right? Plus y squared plus 2y, and again, you take a half of that, square it, and you add it to both sides. And the z, there was no one there, so it's just z squared, right? Now what happens is that this is always a perfect square when you do that manipulation, and it's just going to be x plus a number on the inside here, which is minus 2, all squared. Plus this is y, the number on the inside, all squared. This is z squared. And this would be 4 plus 1, which is 5. Which looks like that. I mean, sure, technically, if you want to be pedantic about the thing, you say this is y minus a minus 1, plus this is z minus 0 equals radical 5 squared. Right? So now you can say I can write it exactly in that form, and I know that form is what we call a sphere, so this is actually a sphere, and I can now say what the center is. Right? Just the numbers that are there. 2 minus 1, 0. Radius is the radical 5. Any questions on that? Calc 3 isn't that bad, is it? Nope, not bad at all. Any questions so far? Okay, let's talk about regions. And again, I want to compare something like in 2D. Let's say I'm doing the region y is less than or equal to x. How do you actually describe that region? Okay, describe these regions to me. What would y less than or equal to x look like? Mm-hmm. So basically you pretend that less than or equal to was equal to, and you know what the graph would look like. Right? This is where the y is equal to x. Since we can be equal, that's fine, we shall include the line. If we couldn't be equal, we would not include the line. Now we want the y value to be less than or equal to the x value. Notice that that will happen below the line. Right. So, in other words, I can describe this as That's how I could describe that region. Give me a similar description for these that I've written on the board.
So the first one would be, you take, starting at the origin, a sphere of radius 2, and then another sphere of radius 3, and it's the space between and including those spheres. So sort of like a...
That is correct. It's sort of a hollow ball, right?
Yeah.
So there's a sphere here of radius 2, there's another sphere of radius 3, and we want the region in between them. Well, yes, the region in between them. So this is 3. This is... Right? So you take a sphere of radius 9, you want to be less than that, meaning you want to be inside that sphere. Then you take a sphere of radius 4, you want to be bigger than that, you want to be outside that sphere. To have both of these requirements met at the same time, it means you have to be in between the spheres. Well, not strictly speaking, it will include the spheres. In this case, it's sort of a similar idea. Except now, you only want the top half of your sphere. So there's a sphere of radius 2, there's a sphere of radius 3. You want everything in between them, but where the z is greater than or equal to 0 means it's above the xy plane. Here, again, it's a similar thing, except now you want the part of your sphere that's below. This is 2, this is 3. I want everything here. What would this guy look like over here? So this would be the whole sphere. But I want the part where the x is less than 0, right? So it means I take the slice over here. I should probably actually draw that bigger so you can see that. Come over here. Drawing shape is actually going to be a very important thing in this course, so just start practicing now when it's a lot simpler. We're going to be drawing more complicated things pretty soon. Here I want the x to be less than or equal to 0, z to be, did I say greater than or less than? That's the x, that's the y, that's the z. Background. I want the part of the spheres that are over here, right? The x is less than 0. Again, this is where the 2 is, this is where the 3 is, this is where minus 2 would be, where minus 3 would be. I want the z to be greater than or equal to 0, which means we're going above. So, right, so that's the object that we have here. Does everyone see that? Does that actually look like something that it should resemble? right? So we're in between spheres 2 of radius 2 and radius 3, but we slice off parts that we don't want. We only want parts where the x is less than 0, so we cut off everything in front of the xz plane. We only want the part where the z is greater than 0, so cut off everything that's below the xy plane, and we're left with that. Pretty soon we're going to know how to integrate over something like that, right? We're not going to be integrating over intervals anymore, that's just too boring now. Huh?
It's a quarter of like a handle, I guess.
Yeah, a whole handball, yeah. Okay, so that's what that region would look like. Okay, so 10.1 is just getting you familiar with how things work in 3D space, which now we've talked about everything I wanted to talk about. The next thing we're going to talk about is vectors. Any questions so far?
Does that mean the homework for 10.1 is due tomorrow?
That's correct. So that's how it's going to work. I just completed section 10.1, so the homework for 10.1 is due tomorrow. Even if I don't say it, you should just know that it's due tomorrow. So 10.1 homework is due tomorrow. And let's actually move on. Anyone taken physics before? What's a vector then? Oh, this should be easy for you then. Soon it'll be just like 10.1. calc203 really isn't bad after all. So what's a vector?
It has both direction and magnitude.
Quantity with both magnitude and direction. There are tons of quantities like this. For example, force, for you physics people, can be thought of as a vector, like the force of gravity, right? That's something that has a magnitude and a direction, for example, right? The direction is always pulling you down towards the Earth, and it's pulling you at a magnitude of 9.81 meters per second squared. Where here we define magnitude to be the magnitude of acceleration towards the Earth, right? So that's a vector, right? So we can pictorially represent vectors by arrows, right? This is called this is the initial point of the vector. This is called, what is that called? Terminal point of the vector. Right. The length of the vector is its magnitude. So if you're working in a certain amount of units and you wanted to represent gravity as a vector, it will be a vector that goes straight down, and its length, you make sure it's 9.81 if you want to measure magnitude in meters per second squared. That's done. Let's see what else. I want to introduce the notation that we're going to be using. Let's say you have a vector where the initial point is called point A. The terminal point is called point B. can just say AB, right, where you just write an arrowhead over the A. Or you can actually name vectors you want. Those are usually named by lowercase letters. And you also put an arrowhead over the lowercase letters, right? So when you're, so this is especially when you're writing by hand, you'd actually use an arrow over something to actually notate that it's a vector. In textbooks, it might just be a bold A. It's going to be very important that we distinguish between things that are vectors and things that are not vectors. There are going to be things that are only have magnitude but no direction. We call these scalars. And vectors have magnitude and direction. They're called vectors. And they don't play well with each other in many contexts. So you're going to have to be able to identify which is which. So you identify vectors with that little notation. Just put an arrow over the head and I'll know you're talking about a vector. Right? And of course, if you write something that you know is a vector and you don't put the arrowhead over it, I'm going to mark it incorrect because it's not a vector and it's supposed to be. Right? So the notation is actually pretty important. And it can cause a lot of confusion if you mix vectors and scalars. Right? They don't always play well together. It's going to be like this for maybe 4 sections or so. We have to get a lot of definitions out of the way, but then we'll start with the interesting stuff right away after that. Yeah, that's vectors. What else did I want to tell you about vectors? I did not introduce that notation yet. Let me talk about scalars then. I didn't have that in my notes, but I should mention. So if you're reading the textbook and you see an A as opposed to an A with a vector over it, it's two completely different things, two completely different objects. They're not the same, right? Or if you see a bold A in the textbook, that represents a vector. The scale would just be a regular faced A. No arrows, no nothing. And I'm actually going to hold you to this notation, which means if you're supposed to write a vector, you don't put an arrow over it. I'm going to mark it wrong. I'm going to be like, you can't do that with a scalar. Okay. And let's talk about combining vectors. You can actually combine two vectors, right? You can add them like numbers, you can subtract them. Multiplication is sort of weird. We're going to deal with 2 different types of multiplication in the next chapter, but it's sort of weird. Let's actually just talk about this. So, reload the scripts. So far we're doing pictures. So, say we have vectors U and V. So let's say you have that vector u here. Right? Then right where u leaves off, you tack v on, and that could be another vector going in another direction. That's fine. Then the vector that is the sum is going to be the vector that starts where u starts and ends where v ends. All right, so if you draw the vector here, this is the vector u plus v. Right? You sort of add them together, add one to the other. Right? There's something called a parallelogram law, where you know that if u is here, and you attach v at the same initial point, then you can actually draw a parallelogram, and then the vector that is the diagonal of the parallelogram is the vector u plus v. Right? So you can think of it in either of these ways, right? So you literally add v to u. U takes you somewhere, and you add v to that position, and you take it to some other position. You say you added the vectors. And this new vector is called the sum. The vector addition. So then, to tell you how to subtract things, we're going to have to define something. The vector minus u So if your u looks like this, your minus u is going to look like that. Right? Exactly the same magnitude, except the initial and terminal points are switched. You go in the opposite way. Right? Now to subtract two vectors, so it's you're thinking of adding the negatives. So if your u is like, so let's say u is like this, and v is like that, right? Then u minus v would be, your u is like this. Now, minus v would actually be, you sort of think of it as u plus minus v. Right? So you add the negative. Now the negative of v is just going to be the vector that flips in the opposite direction. So here's your u, here's your negative v, and you add those, which means your initial point starts here and your final point is there. So this is the vector u minus v. remember I told you scalars and vectors don't always play well together. In terms of multiplication, they actually do. You can actually multiply a scalar by a vector. It was that minus u I can actually think of as minus 1 times u. So multiplication, they're fine. You can't add a vector to a scalar though, but you can actually multiply them. So let me actually define that. I'll make this notation clearer in a bit. So, example, if this is u, then the vector 2u is just going to be a vector in the same direction as u, except it's double the length. The vector minus 2u will be double the length, but it travels in the opposite direction. Did I tell you about vectors? Okay. So any scalar multiple of a vector is actually parallel to the vector. It just might go in the exact same direction or exact opposite direction, but they will actually never meet if they run on forever. So that's what I want to tell you. Okay, but we are not going to work with vectors in picture form much at all. We're going to work with them in terms of components. So let me talk about how to do stuff with that. example, I could describe a vector u in this way. So it's very similar to like a coordinate, except note the sharp brackets, right? Meaning again, as far as notation is concerned, if you write parentheses and you write brackets, they actually consider two different things, right? This is a coordinate. This is a vector. They're actually two different things. You can actually represent vectors very similar to how you represent coordinates, but you use a square bracket to notice that it is a vector. How you actually think of that coordinate you think of this, guys, as how far you're moving in the x and y direction respectively. So example, let's say I'm in 2D, just to get the idea across x and y, and I could represent a vector representing that vector. Now let's say I know the initial point, x starts at 1, the final point, x starts at 3, initial point here is 1, final point here, maybe 4. So if I say call this the vector A, then I could actually represent A using coordinates. And how do I do that? Well, figure out how many units I move in the x direction. I move 2 units to the right. So I put a 2 here. How many units do I move up?
3.
I move 3 units up, so I can put a 3 here. Right? You should notice that the coordinate 2, 3 is going to be like 2, 3. It's actually just going to be a fixed point. Is it going to be on that vector? Right? And the thing is, this vector you can actually move anywhere you want, right? This is still the vector 2, 3. Even if I move it over here, I can move it over here. This is still the vector 2, 3. Right? Because it's saying I move 2 units to the right, 3 units up. So that tells me how to get from the initial point to the end point. And that is that's how the notation works. You can actually reverse things. So for example, I can have a vector that looks like this. Where I know, let's say it moves 2 units this way and 3 units that way. And this vector here, I can call it, it moves 3 in the horizontal direction, and I would say it moves -2 in the vertical direction, right? So this says 3 units right. Right is the positive direction as far as x is concerned. This says 2 units down. And as far as y is concerned, down is the negative direction. A similar vector, I could do this one. This would be the vector -3, -2, right? Because if I move 2 units this way, 3 units that way. Right? We can actually represent the vector using these numbers, and you can sort of have a picture of how that looks. So again, it doesn't have to be at a fixed point. You can have that same vector that moves these distances, and you can have it anywhere in the plane you want. Vectors don't have to be fixed at a particular location. There are some vectors that we like fixed at a particular location. Those are called position vectors. If the initial point of a vector is the origin, it is called a position vector. So I can do the vector 2, 3, and it's called a position vector because it actually ends up at the position you expect it to end up. It will actually coincide with the coordinate 2, 3 will be at the end. Right? So once I fix its initial point to the origin, I call it a position vector. Those are going to be important when we're talking about equations of lines. Let's say how would you actually find that vector? Vector AB. Subtract component-wise, which means you keep things in each component and you always subtract the final minus the initial, which means if you know the final point is given here, you're going to subtract this from that, and you do it component-wise. So you're going to take the A2 minus the A1, that is your new first coordinate, and then you're going to take the B2 minus the B1, That is the second coordinate. And you can also make a note that that's exactly what happened here. Where did I put that eraser?
Question.
Yes.
Oh, why aren't we adding them here? How do you know, like, you know, when we have to?
Well, we're going to explain that with this example.
Oh, okay.
Why don't we add them instead of subtract them? Here I actually did a vector before where the initial point was 1, 1. The final point was, what, 3, 4? Why does it make sense to subtract them? Well, remember we actually want to find the distance that you move in the x direction. Put that in the first coordinate, right? So basically what you have to figure out is what distance did you move to get from 1 to 3, right? Distance, you would just subtract the x values, right? So it's just 3 minus 1 will actually give you the distance you move in the x, right? So you move 2 units right. If you talk about the distance in the y, well, you find the distance between these two, but that is just a subtraction again. You actually subtract the y coordinates. 4 minus 1 will give you the length. We subtract because we're finding the distance between the 2 points. Right? So it's always going to be subtract. So if you were given 2 points, which you're going to be given that a lot, you're going to subtract the final, take the final point, subtract the initial point, and that actually gives you the vector that connects the 2 points, because that's how you find the distance that you have to travel in each direction. We're going to do that a lot, so you should know how to find the vector connecting 2 points. Okay, what else is there to tell you about vectors? Example. So what's the vector that connects those 2 points?
3 negative 5 negative 5.
Okay, let's give this a name for all time's sake. Let's say I call this AB, so the vector AB, and so I put those sharp brackets. I go from here to here, which means this is the final point. I'm going to take final minus initial. 1 minus 4, comma, 3 minus a minus 2, comma, 5 minus 0. So the vector that connects those 2 points is the vector negative 3, 5, 5. So that's a vector that moves 3 units in the negative x direction, then 5 units in the positive y direction, then 5 units in the positive z direction. So for example, if I were to see what such a vector looked like in 3 space, let's say I wanted to make it a position vector, so I'm starting at the origin. What do I want to do? Well, I'd go 3 units back this way, 5 units in the positive y direction, and then I go 5 units in the positive z direction. And so the vector is going to go from the origin to that point. This is the vector minus 3, 5, 5, and if it's a position vector, it will actually hit the coordinate minus 3, 5, 5. So given 2 points, you can find the vector that connects the 2 points. And you can make sure it goes in the right direction by making sure you're taking the final minus the initial. This is actually the vector that will start here. If you put its initial point there, its final point will be here. So that's nice. Next thing we need to do is the length of a vector. Say if A equals A1, A2, some people like to do double bars when they're talking about magnitude of a vector to differentiate it from, distinguish it from scalar absolute values, but you don't have to. Either one you write, I'll consider fine. Is given by and how did I come with that formula?
Pythagorean theorem.
Pythagorean theorem. Exactly. So if I think of that as a position vector, where this is A1 and that is A2, I can think of this as forming a triangle, where if the length of this is A2 and the length of that is A1, then by Pythagoras' theorem, the length of this would be the square root of A1 squared plus A2 squared, by Pythagoras' theorem. So everything I said so far, if I gave you examples with two-dimensional vectors, 2 coordinates, it's same works with 3 coordinates. Not everything works this way, so you should be aware of that. For example, if you're only in 2D, you have a two-dimensional vector, there are really only 2 directions that are parallel to it. If you're in 3-dimensional space, there are an infinite number of vectors that are parallel to any given vector, right? So things actually can be different. But so far, everything I said about 2-dimensional vectors apply to 3-dimensional vectors. We'll talk about differences at a later point. Right now, we just want to get the basic properties out of the way. So I showed you how to add and subtract with pictures. Let's talk about with components. It's sort of done how you'd expect. So it's sort of nice how that works out. So if your A is the vector A1, A2, and your B is the vector B1, B2, then if I take A plus B, that is just the vector A1 plus B1, you just add component-wise. And the vector A minus B will just be A1 minus B then A2 minus B2. And if you're wondering, yes, this actually works out pictorially as well. Meaning if you were to draw these 2 vectors and you were to draw this vector where you just add the components, it will actually form that parallelogram that I spoke about. And same thing with the negatives, right? So the numbers actually work out pictorially. Everything is consistent, so you don't have to worry. But if you don't care about the picture, all you care about is the components, which oftentimes you will, that's how you actually do it. Okay, what else do I need to tell you about vectors? I guess it would be nice if I actually gave some examples. And of course, this extends to 3 dimensions. If I had 3 components, I could just add or subtract component-wise. All right, so addition and subtraction applies to 3-dimensional vectors as well. Sure, why not? In this case, A plus B would be you just add the corresponding components. So you have 1 plus 2, and then you have 2 plus or minus 1. This is 3 comma 1. And so if you wanted to actually draw this, A would go 1 unit in the x direction, 2 units up in the y direction. That is my vector A. the vector b would go 2 units in the x direction, then 1 unit down. And we just found that the vector, if we add them, it will actually go 3 units in the x direction and 1 unit up. So if I actually also draw that as a position vector, I'll get that. This is A plus B. And if we're actually on graph paper and this was the scale and everything, you'll actually notice that this actually formed a parallelogram. What else is there? In general, we'd like take a break like halfway through class, but since we're not really dealing with anything too serious now, we're probably just try to push through it till we get to the more exciting stuff. It's just tedious to write down, but hopefully it's not too difficult to understand. I want to get to the exciting parts really quickly, so let's just get through scalar multiplication. Let's say A is equal to A1, A2, and again it applies to 3-dimensional vectors. Then if I take CA, I multiply component-wise, that's CA1, CA2, and yes, it's consistent with how the picture would work. So for example, if A is the vector 2, 3, then the vector 3A is just going to be the vector 6, 9. And this is a vector, it has the same direction as A, and it's actually 3 times the length of A. Right? So 2, 3 would look like that. This guy, if you draw him, will look like that. And it's in the same direction. Right? We know it's in the same direction because I multiply by a positive scalar. If I multiply by -3, it will flip and go in the opposite direction. Parallel, but the opposite direction. Okay. Now some examples. Okay, work on those. Can you guys actually see over here? -405. So A is the vector 1, 2, 3. B is the vector -405. And I want you to find the magnitude of A plus B, A minus B, 2A, 3B, and then 2A minus 3B. We'll talk about that when we get to it. Let's actually just do these. So what's the magnitude of A? It's radical 14. So the magnitude of A would be the square root, we just follow the formula. Each component squared, you add them together. So it's 1 squared plus 2 squared plus 3 squared. That's 9 plus 4 plus 1. Right? So that's square root of 14. If I take A plus B, that's just the vector. I'm just going to add the corresponding components. So take 1, add it to a minus 4, 2, add it to a 0, 3, add it to 5. This is the vector minus 3, 2, 8. A minus B. Now I subtract corresponding components. So it's just going to be 1 minus a negative 4. It's going to be 2 minus 0. It's going to be 3 minus 5. That's the vector 5, 2, minus 2. The vector 2a is just going to be the vector 2 times 1, 2, 3, which you just multiply them. 2, 4, 6. The vector 3b is just going to be 3 times the b vector minus 4, 0, 5. And you multiply each component by 3. So it's minus 12, 0, 15. Or take the vector 2a minus 3b. That's just going to be this one minus that one, which I already found each. So it's just going to be 1 minus a minus 12, 2 minus 0. I should be looking at this. 2 minus minus 12, 4 minus 0,
6 minus
6
15,
minus 15,
which is 14, 4, 9. 9.
minus 9. Okay, those are some arithmetic operations with vectors. And it all coincides with the pictorial diagram exactly as you'd expect them to coincide. It's just really nice that they work out in such an intuitive way. Here are some more things that are intuitive. Some of the properties of vectors. Addition is commutative as you expect it to be, because you've done it with scalars all the time, and with scalars the real numbers is actually true. It's also associative with addition, which means if you have 3 things, you can add them 2 at a time, and it doesn't matter which 2 you add at a time, it's going to be the same. There's something called a 0 vector. This is a vector with zeros in all components. If you add the 0 vector to any other vector, you just get itself, just like if you add 0 to a scalar, you get itself. Also to be expected, A added to its negative gives you the 0 vector. Scalars can distribute across the sum of vectors, so D times the vector A plus B is just D times A plus D times B. Vectors can distribute across the sum of scalars, so you have D plus E times A, this is just D times A plus E times A. Multiplication, you can actually choose who you multiply by, there's associative property with multiplication, and the scalar 1 times the vector A is actually equal to A. So, some of you might be wondering why we're writing it down. Well, those of you who are math majors here will appreciate this later on when you take linear algebra. Not everything is always so obvious. There are cases where addition is not commutative and where all this doesn't work out, where 1 times A is not A, the 0 vector is not where 0s is everywhere, and et cetera, right? But here, everything is nice, and it works out sort of like how we expect it to work out. So the 3D coordinate plane is a very nice plane. It's a very nice space to work with because a lot of our intuitions still work. I just want to make that comment because there are sometimes I'm going to write things down and they're going to be like, obviously. It's not really obvious. Like everything had to be proven. And there are cases where the obvious thing is actually wrong. Here it's not though. Yeah, so those are properties of vectors, right? These can actually work out. More notation. I think this ends the notation stuff. I mean, after this, we're going to be doing some interesting stuff in 10.3. Don't know if I'll get to it. Standard basis vectors. There's the vector called I, which is the vector 1, 0, 0. There's the vector called J, 0, 1, 0. There's the vector called K, 0, 0, 1. I, J, K are the basis vectors. These are basically the vectors that run along the coordinate planes, and they all have length 1. So the vector I actually runs along the x-axis. Vector J runs along the y-axis. The vector K runs along the z-axis, and they all go to the coordinate, or it's just one distance away. So it's just 1, 0, 0. This goes to the point 0, 0, 1. Now the cool thing about these vectors is that you can actually represent any vector in terms of these vectors. So let's say A has components A1, A2, A3, right, in 3 dimensions. It turns out I can write this as where this follows from how we add vectors and the fact that the 0 vector exists. It would not be true if those things too were true. We can actually take the A out as a scalar. Here we can take A2 out as a scalar. Here we can take A3 out as a scalar. And so this guy I can write as I, J, K. This actually gives you an alternative notation. This is called the IJK notation for vectors. So you actually might see vectors represented in 2 different ways. Sometimes they'll tell you components, sometimes they'll tell you the IJK notation. example, the vector 2, 3, minus 4 equals the vector 2i plus 3j minus 4k. Right? You can write one or the other. They actually mean the same thing. Don't mix the notations. If you're using brackets, you shouldn't have ijk. If you're using ijk, you shouldn't have the brackets, right? So if I see anyone writing something like 2i plus 3j minus 4k, and then you put the brackets there, no. I'll mark it wrong and I'll say, I don't understand what you're talking about. Or if you do something like, I don't know, 2i and then 3j and then minus 4k, no. Right? Use one or the other. Either you write it like this or you write it like that. Personally, I like writing it like this, but you don't have to write it that way. Right, so those are called the standard basis vectors, and they're called standard basis vectors because a standard basis is a set of vectors that you can express any vector in terms of those vectors, and that's what we can do with ij and k. Okay. Maybe I should do an example where we actually work with the ijk notation. So you can use whatever notation you want, but if the book actually gives you either notation, you should recognize them. So who knows what a plus b is in this case? Yeah.
Minus 3 unit vector I plus 2 unit vector k plus 8 unit vector k.
Yep. You same as before. You sort of add the components together, except now you're identifying the components by I, j, and k. You should also notice that this guy is equal to minus 4i plus 0j plus 5k. I didn't write the j, it just means its component, its scalar coefficient is 0. So then here you add corresponding components. So you add 1 minus 4 plus 2 plus 0. Plus 3 plus 5k. So this is minus 3i plus 2j plus 8k. Similarly, a minus b is just going to be this minus that. It's 5i. 2 minus 0, 2j. 3 minus 5, minus 2k.
These are the same as we had in the last example.
Yeah, it's the same as the last example. It's just alternate notation. That's really all it is. It's not going to be any different. So 2a is, as you would expect it to be, you just double all the components here. So that's 2i plus 4j plus 6k. And you can notice that, yes, this actually coincides with what we actually did before. This is actually minus 3, 2, 8. This is actually 5, 2, minus 2. This is actually 2, 4, 6, which corresponds to our previous answers. More definitions. By the time we get out of this, you're going to know everything about vectors. Well, vectors in R3 and there are things called unit vectors. These are just vectors with magnitude 1. Unit vectors, just like the unit circle is a circle of radius 1. So how do we find a unit vector? Basically, you use scalar multiplication. You often use U for unit vector, and all you do is you take the vector that's not 0 and you divide by its magnitude. Right? This sort of scales it down to have a distance, a length of 1. So, example, A is 1, 2, 3. I made it a little bit more interesting. 2 minus 1, 3. Okay, thoughts?
Would they have to be like 4 minus 1, 6? No.
4 minus 1, 6.
Yeah.
Just divide across root 14.
Divide by root 14. We actually found the magnitude of that vector before. Here, the magnitude of A is just going to be the square root of 2 squared plus minus 1 squared plus 3 squared equals radical of 14. This implies one unit vector is just going to be A divided by its magnitude. which is just going to be vector 2 minus 1, 3, divided by radical 14, which I can write as 2 over radical 14, minus 1 over radical 14, 3 over radical 14. And you can actually check if you find the magnitude of that with the same formula, you'd actually get 1 as the answer. Another unit vector would be which vector? Yeah.
You can negate all of those components.
The negative. It's still parallel, it just goes in the opposite direction. So this is just the negative of 2 minus 1, 3 divided by radical 14, which is minus 2 over radical 14, positive 1 over radical 14, minus 3 over radical 14. Let's talk about some applications. I mean, so far this is all abstract. It just seems like we're playing around with numbers in these fancy brackets and commas in between them. By the way, don't forget the commas. Like, if you forget the comma, I'll grade you down for that. Stickler for notation. Make sure your arrows are where they're supposed to be, commas are where they're supposed to be. Make sure you have sharp brackets when you're talking about vectors, as opposed to curly brackets, etc., etc. Because a lot of these things are really dangerous if you mix the wrong things together. So really be a stickler about your notation. Talk about applications. Here's an example. Physics has a lot of good applications for vectors, so let's actually find that. Some physics applications. Retention forces. Yes, we can use tension. Right? So let's say we have an object here that's a 50-pound weight. It's being held in place by 2 ropes connected to the roof, where this one is T1, that one is T2. Let's say we know the angle here is pi over 4. We know the angle here is pi over 3. And I want to know the tension forces. How much force and in what direction must this T pull and that T pull in order to keep this weight stationary? For this application, you're also going to see something else that I had you do in the quiz yesterday. And that's where I said, oh, if you know a right triangle has this side length, how can you describe these other 2 side lengths in terms of theta and the magnitude of one side? You're going to need that concept here. Okay, ideas. Hmm? A free body diagram. Not anything that complex. Yes, so we know that 50 pounds is pulling down. We call that vector the weight vector. Right? So I can think of W as the vector. How could I describe that vector?
If we're in, say, 2 dimensions, it would be 0, negative 50.
0 minus 50. Right. Okay, so basically what I want to do is I want to write this as a vector. I want to know this is what, comma, what, and this is what, comma, what, right? That's the whole point, right? Where I can know the magnitude of that vector is how much force this rope is pulling with. The magnitude of that vector is how much force this is pulling with. And the vectors themselves actually tell me what directions they're pulling in. Right? That's the whole idea. That's what I'm asking for. Right? So we can know that the weight is actually that guy. Now what do we know? What would the magnitude of these vectors be? know they add up to 50, but let's work on one at a time. How do I know the magnitude of T1? Give me some expression for it.
It would have to be,
The vector W minus the T2.
Okay, so I don't know what T1 and T2 is, right? So if I write an equation with T1 and T2, how's it going to help me? I have two unknowns, yeah?
Oh,
So,
yeah, no, go ahead.
Okay, ladies first, I guess.
okay, so we draw a triangle from the initial point of T1 to the 50 pound.
Alright, so here, put in the right triangle there.
Yeah. And now we,
You know that this angle is pi over 4, right? Do you know this angle?
it's about
It's also pi over 4, right? That we know from high school geometry, angles cutting the transversal, blah, 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 right? Okay, so I know that, right? I don't know what the length of this line is, but I know it's going to be the magnitude of T1, right? Whatever the magnitude of T1 is. And I told you yesterday, if you have a right triangle where you know the magnitude of the hypotenuse and one of the acute angles, how do you find the magnitudes of the other two sides? Which is what we need after all, right? I need to put the magnitudes here and here. So how do you find the magnitudes of the other two sides if you know this angle? You're going to use sine and cosine. So I know, in the example yesterday, the hypotenuse was b, the acute angle here was theta, and I asked you, what is the length of this guy? And what is the length of that guy? What was the length of this guy?
sine,
B sine.
It was b sine theta, right? Which technically, absolute value would be, to make it technically correct, this would be b cosine theta. That was the answer, right? If you didn't put absolute values, I made you get away with it, because the way we described it, obviously, it was positive, right? So here, what's happening? Theta is actually pi over 4. I don't know what this magnitude is yet. I want to actually solve for that. So what do I know about this guy? So how could I actually describe T1? That's the question. Right, there's going to be an x-coordinate and a y-coordinate. Right? So if I think of the origin as being where this weight is, that's what we're going to do. Right? So, yeah, what you were saying?
You could write the x as T1 cosine of pi over 4.
Right, this is magnitude of T1 cosine of pi over 4. However, notice that we're moving to the left here, right? This is the origin, we actually move to the left. So that's going to be the negative. Right? And what about the vertical? Well, that's going to be T1 sine of pi over 4. Right? What's cosine of pi over 4? So this minus radical 2 over 2 T1 magnitude. And this is positive radical 2 over 2 T1 magnitude. This I can actually write as radical 2 over 2 times minus T1. The ultimate goal here is we're going to find what T1 and T2 are, their magnitudes. Okay? And a similar thing can happen for T2. So now if we focus our energy on T2, so the triangle here, this would actually be pi over 3, which is what I think I made pi over 3. Yes, pi over 3. Then the components T2 would be, the horizontal component is going to be the cosine. So that's just going to be T2 cosine pi over 3, comma, so that's moving to the right, so it's positive, right? This one is moving up, so that's also positive. So this is going to be T2 sine pi over 3. What's cosine of pi over 3?
1/2.
And sine of pi over 3?
1/2.
What?
1/2. Radical 2.
So I know the vector T2 is just going to be the vector Now, of course, the system is in equilibrium, right? If it's holding up the weight, it means that the forces that is going up should be equal to the force that is going down. That's why it's staying stationary, right?
Right, oh, okay.
Huh? Right? The force that I'm pushing up with
Yeah.
must be equal to the force that I'm pulling down with, right? That's why, right? If that wasn't the case, it would actually fall or shoot up into the roof. So what do we know?
So,
This means since we are in equilibrium, T1 plus T2 must be equal to what?
W.
Must be equal to W?
No, to negative W, duh.
Equal to negative W, right? W is pulling down. These two forces are pushing up to keep the weight balanced. So it has to be going in the negative direction of W, which means that if I add these two vectors together, I should get the negative of that vector down there. So what does this mean? If I take that component, add it to this component, which means I have T2 minus radical 2 over 2 T1, comma, I have radical 2 over 2 T1 plus radical 3 over 2 T2. That should actually give me 0.50. So this means minus radical 2 over 2 T1 plus 1 over 2 T2 is actually equal to 0. And I know radical 2 over 2 T1 plus radical 3 over 2 T2 is equal to 50. Now I have two equations, two unknowns. I can actually solve for these guys. Did I actually write down the question?
Yes.
I did write down
No,
the
you
question.
didn't write the question down. You
Find the
just,
tension forces T1 and T2.
you just drew the picture.
All right.
Yeah.
Just want to make sure. Okay. All right. So how do we solve that? Back to algebra, simultaneous equations. Yeah, you can add the one equation to the second, right? Because these are the same except opposite sign. If you add them, you kill them. So this is equation 1. That's equation 2. Then I can just add these two. That's radical 3 plus 1 over 2 T2 is equal to 50. This is equation 1 plus 2. This means that T2 is equal to 100 over 1 plus radical 3. Since I also know now that minus radical 2 over 2 T1 plus a half T2 is equal to 0. This means if I know this guy, I can just plug it in. Plus a half of that. So this means that T1 is equal to 50 over 1 plus radical 3. It'll be negative when I move it over that, and then I multiply it by 2 over radical 2. So T1 would be that. Thus, the tension forces are where are the tension forces? T1 had what components? I believe I wrote it down over here. What was it?
Negative T1, T1 multiplied by negative 2 over 2.
It was radical 2 over 2 times minus T1 magnitude, right? Was that it? Okay, so T1 I actually know what it is. This is 100 over and then this was actually magnitude of T1 here, right? Right, which this I actually could simplify. So this is actually 1 over radical 2, multiplied by radical 2, I get 2, so this is just minus 50 over 1 plus radical 3, comma 50 over 1 plus radical 3. T2 was the vector a half magnitude T2, so it's a half of this. Comma radical 3 over 2 times this. So those are the actual tension forces. This, with the vector you can tell their direction and the magnitudes you actually found. These pull forces 100 over radical 2, 1 plus radical 3 pounds, and 100 over 1 plus radical 3 pounds, respectively. boat being pulled by 2 tugboats in opposite directions. So, one. Where would the big boat actually move, right? So let's say one tugboat is tugging at an angle of pi over 6, and it's actually moving at a speed of 5 meters per second. The other tugboat is tugging at an angle of minus pi over 4, and its speed is 2 meters per second. I want to know what direction will the tugboat move in, and with what speed. And with that example, we'll actually end 10.2, so the homework for 10.2 is also due tomorrow. And I hope yesterday's quiz inspired you guys to actually start looking over your old material, because tomorrow we have another quiz on calc2 and below. So actually yesterday's quiz won't actually count your grade, just think of it as a diagnostic exam, which is good for some of you. And so tomorrow we'll give you the real deal quiz for previous material. Make sure you remember your Pythagoras there, make sure you remember your trig, how to differentiate, how to integrate, how to draw different things. Remember stuff about polar coordinates, because it's all going to come back. Right? So, with a vengeance, polar coordinates in 3 dimensions. It's called cylindrical coordinates then. It's going to be, yeah, you're going to have to remember all that stuff. So tomorrow I'm going to give you that quiz, and then we continue. I'm not sure if I'll do the MATLAB tomorrow. Maybe just push that off. But the MATLAB homework is due, so that's also due tomorrow. Oh, so just make sure, can't say I never told you. Tomorrow. Homework section 10.1, 10.2, and MATLAB section 1.3. I think I assigned problems 1.1 and 1.3, right?
Yeah.
Yeah. So that's all due tomorrow. But before that, let's solve this problem and get out of here. How would you actually solve that? To use the language of physics, there's something called a resultant force, which means if there's one force pulling that way, another force pulling that way, then the result is actually going to be the sum of these forces. Right? So we're after that vector. How do we find the components of that vector? And yeah.
Does that mean you want the angle? Like when you use the direction to use angle?
No, I mean, you can give me as a vector.
Oh, okay.
If they wanted an angle, they would specify it, but if not, you can give it as a vector. Okay? The boat will move in this direction. The magnitude will give its speed. So that's another example of vectors and scalars. Velocity will be thought of as a vector and speed will be thought of as a scalar. So the velocity is actually the vector itself. The speed is going to be the magnitude of the vector. And it's actually going to be the resultant vector. But what do you know about the resultant vector here from the picture? I drew it in a very suggestive way. It's going to be the sum of the other two vectors. So all I need to do here is figure out what are the components of these vectors, add them together, and that's where the boat's going to move. And if I find the magnitude of the vector, that's going to be the speed with which it's going to move. So how do we get at those components?
Using sine and cosine and the angle.
Exactly, trigonometry. Pretend where the boat is connected is the origin, and then we're going to actually use sine and cosine to figure out these components. Say we're on the xy plane, there's one guy going here. I know that the angle is pi over 6. Right, so I want to figure out what is the magnitude and direction of that. Right? I actually know what the hypotenuse is, right? It's 5. So if you have a right triangle, you know the magnitude of the hypotenuse, and an acute angle, how do you find the opposite side? 5 sine theta. Sine of pi over 6 is? You asked that like it was a question. You're not sure?
No, I thought this was good.
Cosine of pi over 6 is? So, let's say here we have tugboat 1. And here, down here we have tugboat 2. So, direction of tugboat 1 is just going to be x is moving positive in this way, so it's 5 radical 3 over 2, comma the y, which is just 5 over 2. That's that vector. Similarly, if I focus on the second tugboat, I know that the length there is 2. I know that the angle here is minus pi over 4, but you can sort of ignore that for the most part. Well, you don't have to. So the length here would be, it's the opposite to that, so it's going to be 2 times the sine minus pi over 4. The length here is the adjacent side, so that's going to be 2 times the cosine of pi over 4. So direction tugboat 2 is going to be, the x is going to be 2 cosine pi over 4. What's cosine of pi over 4?
2 over 2.
Radical 2 over 2. The 2's would cancel, so that's just radical 2. Sine of minus pi over 4?
Negative root 2.
Minus radical 2 over 2, so it's just minus radical 2. Alright, so you move to the right and down, so you expect this. So direction will move in is, you just add these guys now. So it's 5 radical 3 over 2 plus radical 2. And 5 over 2 minus radical 2. Its speed would be equal to meters per second. And that ends today's lecture.
Oh, that is good.
Sort of tedious, but it was necessary. 10.3 is slightly more interesting. 10.4 is slightly more interesting. Still, 10.5 is where the fun begins. But also sort of elementary. Oh, 10.6 is going to be a lot of fun.